Hello, welcome back. Okay, so here we have a setup of an electrolytic cell that's used to electroplate an object, in this case a spoon, with a silver coating. So we start off with the spoon. Amongst the components in the solution, we have some silver ions. And so what we have happening is we have a layer of silver ions taking an electron from the power supply and depositing a layer of metal over the silver spoon. So we're going to look at electrolytic cells in this lesson. So this lesson is electrolytic cells. In this lesson, we're going to look at the common design features and general operating principles of commercial electrolytic cells, and the selection of suitable electrode materials, including the silver that we just saw as the anode in the previous example, the electrolyte including its state, and the electrolyte we had in the silver plating cell was silver aqueous ions, and any additives that result in a desired electrolysis product. But note that you are not expected to remember the details of any specific cell in the VCE course. Okay, so let's start off by looking at the design of electrolytic cells. So they have an external direct current source or power source, and we can draw that in our silver plating cell as a short line to represent the negative terminal of the power supply, and that's connected to the cathode, and the cathode in this example is our spoon. So it might have started off as a coppery colour, and then after electroplating it's got a silver coating over the top. The positive terminal of the power supply is connected to the positive electrode, which is the anode. So the cathode, we are forcing electrons from the power supply onto the cathode. So the cathode in an electrolytic cell has a negative charge, and the anode in an electrolytic cell has a positive charge. So the power supply is shown in this diagram. We are forcing electrons from the negative terminal onto the cathode, making the cathode have a negative polarity, and the electrons always flow from the anode through the power supply towards the cathode. So the electrons are leaving the site of oxidation. So that's where electrons are being produced, and then they flow back into the power supply and back through the wires. So electrons always flow from the anode to the cathode, and the electrons only ever flow through wires, through the external circuit. Now, we can use ANOX and red cat to help us with this, help remember. So ANOX stands for oxidation at the anode, and red cat stands for reduction at the cathode. And it doesn't matter if we're talking about a galvanic cell, a fuel cell, or an electrolytic cell, red cat and ANOX always apply. What's different about an electrolytic cell is that the cathode is negatively charged because we're forcing electrons from the power supply onto that electrode, and the opposite polarity for the anode to a galvanic cell, so the anode in an electrolytic cell is positively charged. The longer line in the positive terminal of the power supply, and the shorter line is the negative terminal. An electrolytic cell is a cell that facilitates electrolytic or non-spontaneous redox reactions, and that's why we need the power supply to force that reaction to occur. Okay, so it's really important that we get the polarities right when we're talking about cells. The polarity in an electrolytic cell is opposite to what it is in a primary galvanic cell. So in an electrolytic cell, electrons are forced to flow onto the cathode from the power supply. So we're forcing electrons out of the negative terminal of the power supply onto the cathode. That means there's a build-up of negative charge, so the cathode is negatively charged. Just remember this is opposite to a galvanic cell, where in a galvanic cell the cathode is positively charged, but electrons produced at the anode are attracted towards the positive terminal because they're negatively charged, so they flow towards the positive terminal, they flow through the power supply and then get pushed back onto the cathode for another circuit. So at the anode, we've got electrons forming, which are attracted to the positive terminal of the power supply, and at the negative terminal of the power supply, we're forcing electrons, so we're forcing them into reduction equations. The electrolyte, the positive ions, the metal ions, migrate across to the cathode where they react with the electrons to deposit a metal. So we deposit, in this case, a metal at the cathode. Polarity, when we're talking about cells, is the overall charge of an electrode. Okay, in a galvanic cell, the cell is divided into two separate half cells. But in an electrolytic cell, both electrodes are immersed in the electrolyte. What we need to do in an electrolytic cell is keep the products of an electrolytic cell, keep them separate, because the products will spontaneously and sometimes even dangerously react. So sometimes a mesh, there's a steel mesh here, is used to keep products separate. At other times, inlets and outlets into a commercial cell are used. So here we've got the inlet for our molten NaCl to be poured, and that comes down. And then we're producing liquid Na metal, so Na liquid. This is in the absence of water. At the cathode, we have molten sodium ions that collect an electron and form molten sodium metal. The molten metal is less dense than the molten sodium chloride, so accumulates through these pipes, and then it can be collected through the sodium outlet. Over here, we have at the anode, we have chlorine gas forming, and the bubbles of chlorine gas get taken up by this outlet and the chlorine's extracted. But by doing this, keeping the outlets and inlets separate, the chlorine and the sodium are not able to get in contact, so they're not going to spontaneously react and cause an explosion. Now, just note that the study design states you don't need to know the details of any specific electrolytic cells. So this is the down cell that's used to produce chlorine gas and molten sodium. You don't need to know that. If you had a question about this, the question would give you the details that you need to answer. Okay, now we've seen the electrochemical series before when we've studied galvanic cells and fuel cells. Standard electrode potentials, which are given in the electrochemical series, are given the symbol E superscript 0, which means in standard conditions. So it's volts at 25 degrees Celsius and 1 molar solution for electrolytes. And it's all relative to the standard hydrogen electrode, which is here at 0. So that's the calibration point. Now, when we looked at galvanic cells and fuel cells, we identified the strongest oxidizing agent and the strongest reducing agent. We're going to do that same thing for the electrolytic cells. So the strongest oxidizing agent is found towards the top left of the electrochemical series, and the strongest reducing agent is towards the bottom right. But instead of having a negative gradient between the strongest oxidizing agent and the strongest reducing agent, in electrolysis we have a positive gradient. So if we identify the species that we have, in this case we've got Pb2 plus aqueous, we've got water as a reducing agent as well, and bromide ions. Now we have a positive gradient between our strongest oxidizing agent, which in this case is Pb2 plus ions, and our strongest reducing agent is bromide ions, We have a positive gradient, meaning we need to put in energy in order to make this reaction occur. It's non-spontaneous. So what we do is the required minimum voltage is the E naught of the oxidation reaction, which is this top one here, plus 1.09 volts, minus the E naught of the reduction equation, in this case, negative 0.13 volts. That means we need 1.22 volts is the difference in the E naught values. But we need more than the amount of energy predicted or voltage predicted by the electrochemical series. So we need a more than sign, more than 1.22 volts. And that's to account for internal resistance within the electrolytic cell. So they need more voltage than the minimum predicted by the electrochemical series at standard conditions. So always use a greater than sign when writing minimum voltage required in order for working out the amount of voltage that's required for an electrolytic cell. Okay, the greater voltage is required due to the energy lost in the cell, typically as heat, due to resistance in the wires. In galvanic cells, the most positive E naught is reduced. However, in electrolytic cells, the most positive E naught is oxidized. But we still subtract the lower E naught from the higher E naught. But don't forget the greater than sign. Okay, so let's have a look at an example. An electrolytic cell contains inert, which means non-reactive, graphite electrodes. It contains 1 molar aqueous lead ions, lead-2 ions, Pb2+, and bromide ions. And we've also got water present. So we're circling lead-2 ions, water, 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 and bromide ions. The strongest oxidizing agent is the lead-2+ ions. And we know the strongest oxidizing agent will be reduced, so this reaction will go forward. The strongest reducing agent is the bromide ions, and they're going to be oxidized. We've got this positive gradient indicating that we need to put electrical energy in order to force the reaction to occur, but we need more than the difference in the E naughts. So we take the E naught of the oxidation plus 1.09 volts, we subtract, and in this case we've got a negative sign. We subtract, so we've got negative, negative, which makes a positive. So we end up with 1.22 volts, but we need more than that 1.22 volts. Okay, when we have 2 or more oxidizing agents or 2 or more reducing agents, the strongest agent will react first. So the strategy I recommend is to circle all the species that you have. So in this cell, we've got lead-2+ ions, nickel-2+ ions, cobalt-2+ ions, and water. So circle all the oxidizing and reducing agents present. Identify the strongest oxidizing agent, which in this case is this Pb2+. The strongest reducing agent in this case is the water, and you can see we've got this positive gradient here. So the strongest oxidizing agent will be reduced and the strongest reducing agent will be oxidized. So we need 1.23 minus 0.13 is more than 1.36 volts in order for that reaction to take place. Once the concentration of the strongest agent decreases, then the next strongest agent half reaction will be favoured. So after the lead-2 ions, then nickel-2+ ions will be reduced, providing we've got sufficient power source. And then after that, the cobalt will be reduced. So the strongest oxidizing agent will be reduced first, then the next strongest oxidizing agent, then finally the weakest oxidizing agent. We've only got one reducing agent, so that's the water, and that will be oxidized at the anode. So that reaction will go backwards. Okay, so we've worked out the order that the oxidising agents are going to be reduced, but what would that look like at the cathode? So if we just draw our cathode, the first reaction, the strongest oxidising agent, we're going to get a layer of lead where the cathode is immersed in the electrolyte. Then we're going to get a layer of nickel. And then finally, on top of that, we're going to get a layer of cobalt. So the cathode will be coated first in lead, then in nickel, and then in cobalt. Okay, so when we're selecting electrolytes, the first thing we need to do is locate the water half reactions if we've got aqueous conditions. So we've got water, water, and water here. If the desired oxidising agent is a stronger oxidising agent than water, and for example here we have Pb2+, it's a stronger oxidising agent than water. The strongest reducing agent is lower down than water on the right-hand side. Then it doesn't matter that we've got water present because the bromide ions are a stronger reducing agent and the lead 2+ ions are a stronger oxidising agent than water. So we can leave the water there and it won't react. So that means an aqueous electrolyte can be used because our strongest oxidising agent will be reduced, so we'll have lead metal forming at the cathode and we'll have bromine liquid forming at the anode when it's oxidised. This, by leaving the water there and having an aqueous electrolyte, will be cheaper and safer to run than using a molten electrolyte where we have to exclude water. So for an example, an electrolytic cell contains inert graphite electrodes, in other words, they're non-reactive, and a 1 molar aqueous solution of lead 2 ions and bromide ions. What are the predicted reactions? Well, we circle all the species that we have. We've got lead 2 ions, we've got water as oxidising agents, we've got water, water, and bromide ions as reducing agents. The strongest oxidising agent will react with the strongest reducing agent. We've got our positive gradient. So as long as we put enough energy in the difference of 1.09 minus 0.13 volts. So if we have more than 1.22 volts, then they're the predicted reactions. This going forward, this going backwards. Okay, so we've got lead being deposited at the cathode. So this is our reduction half equation. The oxidation half equation is the reverse. So we have bromide ions forming bromine liquid and 2 electrons. That's the oxidation. Then we add all the reactants together. We add all the products together. We cancel out the electrons and we're left with our overall electrolytic redox reaction. Okay, so when we're choosing electrodes, we need to think about whether we want our anode to react, to be oxidised. If the aim is to electroplate a metal onto the cathode, then the anode can be oxidised to replenish the electrolyte. So in the example that we had earlier, where we have our power supply in our circuit, and we have the cathode being the spoon, and we've got silver ions grabbing an electron to produce silver metal at the cathode. At the anode, if we take silver metal, we can oxidise it, and so we will see over a period of time, we will see that it corrodes, so actually forming Ag+ at the anode. So an ideal anode would be the metal that you want to electroplate onto the cathode. So you're replenishing the electrolyte. When making predictions, so if we've got the electrochemical series, we would want to circle silver metal as well as silver ions. Okay, we can also use inert electrodes that won't participate in the reaction. And sometimes we don't want the electrodes to be reacting. So then we need to choose a suitable material. We need a conductive solid, and examples include graphite, which is a form of carbon, or platinum, but platinum tends to be more expensive. So not often used in the school laboratory. So if we've got inert electrodes, then if we had pure water, then water would be oxidised at both the anode and reduced at the cathode. And so our overall reaction would be, we'd multiply this by 2. So we would have 2H2O liquid plus 4H2O liquid plus 4 electrons to produce O2 gas, 4H plus ions aqueous, 4 electrons, H2, 2H2 gas, and 4 hydroxide ions aqueous. Then we would cancel out the electrons. We would simplify. The 4H plus would react with 4OH minus to produce 4 waters, and then those 4 waters will cancel out, and we'll end up with an overall equation of 2 waters react to produce oxygen gas and hydrogen gas in our solution. Okay, additives can be used to improve the efficiency of electrolytic cells. For example, they can be used to reduce the melting temperature of an electrolyte that needs to be molten or in liquid form. And a good example in Victoria is the Hall-Héroult cell, which is used to smelt aluminium metal. By adding the compound cryolite, which is Na3AlF6, it lowers the melting point of pure aluminium oxide from more than 2,000 degrees to 940 degrees Celsius, which is still hot, but obviously doesn't take as much energy. So that saves energy and is also safer for the people working in the plant. So if the aluminium is dissolved in cryolite, it reacts with 3 electrons to produce molten liquid aluminium at the cathode. And the oxide ions also dissolved in molten cryolite, they actually react with carbon. So in this case, carbon is not inert, it's actually taking part in the reaction. And we produce CO2 gas and 4 electrons. So overall, we multiply the first reaction by 4, the second reaction by 3. Our overall reaction is molten aluminium in cryolite reacts with 3 carbons to produce 4 aluminium metal liquid and 3 CO2. So in the lab, we often use graphite electrodes because they're inert. The Hall-Héroult cell is an exception. Carbon anodes actually take part in the reaction and they combust to form carbon dioxide, which is another problem for carbon dioxide emissions in the electroplating of aluminium. The molten aluminium is extracted, the carbon dioxide and other gases are evacuated, and the molten aluminium is extracted for use to cool and then be used as aluminium solid. Okay, lithium metal is manufactured by electrolysis of lithium salts. Which of the following would be the best choice for the electrolyte and the anode in a commercial cell? Have a go at that question. Okay, if we have a look at the electrochemical series, water is a stronger oxidizing agent and reducing agent than molten lithium chloride. So lithium chloride solution won't end up in the desired product of lithium metal. So it can't be option A or C. Also, we want a carbon rod because we don't want the carbon rod to react. So option D is our best answer. Molten lithium chloride as the electrolyte and an inert carbon rod as the anode. Okay, we've learnt a lot in this lesson. Let's summarise what we've learnt. The anode and ox is always the electrode where oxidation occurs. It has a positive polarity in an electrolytic cell and it can be inert or reactive. The cathode is the site of where reduction occurs. It's negative polarity in an electrolytic cell, and it can be inert or reactive. The power supply is an essential part of the electrolytic cell. It supplies energy to overcome the activation energy, and we need more than the predicted E0 using the electrochemical series. The predicted E0 we get from the E0 of the oxidation minus the E naught of the reduction with a bit more oomph to get the reaction to go. We can use an aqueous electrolyte when water is a weaker oxidizing and reducing agent than the other species present. This gives the benefit of being able to operate at standard laboratory conditions and is used in preference for energy saving to a molten electrolyte if it's possible. Molten electrolyte is used when water must be excluded. It does require a lot of energy to melt the ionic compound. It's more expensive and more hazardous than aqueous electrolysis, but we can use additives to help reduce the melting temperature. Products of electrolysis must be kept separate to prevent spontaneous and potentially dangerous reactions occurring. And the energy transformation in an electrolytic cell is using electrical energy to transform to chemical energy. Next lesson, we're looking at secondary cells. See you then. Bye.